Our speaker today is Will Chapman. Will got a Bachelor's of Science in Environmental Engineering at the University of California, San Diego, a Master's in Civil and Environmental Engineering at Stanford, and a PhD in Oceanography from Scripps in 2021. He then went to the Advanced Studies program at NCAR for a couple of years as an advanced ASP postdoc. And as of this last August, he got promoted to a Project Scientist 1 at NCAR. His research interests are weather and climate predictability, climate dynamics, air-sea interaction, machine learning and deep learning, numerical weather prediction, and post-processing numerical weather prediction forecasts. So with that, I'll turn it over to Will.
Awesome. Yeah. Oh, wow. What a cool room. It's amazing. So again, like Dale said, my name is Will Chapman. I'm from the National Center for Atmospheric Research. It's an NSF-funded institute. I work in the Climate and Global Dynamics group, particularly working on a lot of methods to try to improve CSM, or our global climate model there. It's really an honor to be here. I'm really excited to chat with y'all. So today we're going to be talking about advancing weather and climate prediction with data-driven methods. And I think the room is kind of skewing this direction, so I'm going to be talking a lot over here and ignoring over there a little bit. Sorry. So let's get right into it. I'm going to frame up the problem. I gave this practice talk a couple times, and folks were worried that the text would be too small. I didn't imagine a screen this big, so I'm really happy about that. So I want to start with just framing up the problem. How can machine learning aid in Earth system prediction? And I'm going to frame it up through the lens of numerical weather prediction. So advances in numerical weather prediction, or NWP, or how we forecast the weather, have resulted from a steady accumulation of scientific knowledge and technological advances over many, many years. And the impact of NWP is amongst the greatest of innovation in the physical sciences. The fact that we can predict the weather, and it has such dramatic economic and safety signals, I think can't be understated. And this is a figure by Schultz et al., sort of showing the process by which we predict the weather, in which we're taking some sort of observational system, using some DA to map it towards an Earth grid, using a forward operator in which we're understanding sort of the physics, encoding the physics of the atmosphere. And eventually it ends up as an end user product that is translated so that folks can leverage the product. And because we sort of have a diverse room, I want to be very clear about a couple things. So I've gotten a lot of clarifying points between machine learning models and physics-based models. So the models I'm describing here are physics-based models. We know the equations of motion of the atmosphere. We know how to solve these tendency equations. We just don't know how to solve them analytically, solve them numerically. So what we do is we take the current state of the atmosphere, we discretize the Earth, we solve the resolved dynamics, and then we solve the subgrid dynamics with some sort of parameterization schemes, and then we march forward the physics of the atmosphere. We march forward the tendency state of the atmosphere. And I'm showing just a document from ECMWF, or the European Center for Medium Weather Range Forecasting, showing sort of this complex process. And it's really an amazing feat that we've been able to encode these systems and thus forecast the weather. And the good news is we've been getting better and better at this over time. So this is a figure by Bauer et al. Showing forecast skill on the y-axis. And on the x-axis is our improved skill at forecasting the weather throughout the ages. And what you can see is that we are steadily getting better and better at forecasting the weather. However, as a computational problem, global weather prediction is amongst the most intensive available to us. And it's happening many times at weather centers all across the world. And we're trying to figure out how to improve this process. So better physics-based forecasts require somehow improving our models. So there is some difficulty in this. I work at a center where we're trying to improve the physics representation of the atmosphere. And it is a long and arduous process, and there are many brilliant people working on it. But it takes years and years to develop. Additionally, there's some evidence that increasing the resolution and thus getting out of some of these, resolving some things that before we had to parameterize could improve the predictability, but at a certain point, this becomes computationally prohibitive. And this is really where I see machine learning stepping in to help accelerate this revolution of NWP. So ML methods are being deployed to accelerate this revolution of NWP and overcome some of these limitations offered by examining data directly rather than encoding some advanced physics scheme. So thanks to hardware advances like GPUs, we're able to launch mini ensembles. We're able to increase our resolution. And there is really a attraction from the community toward these machine learning methods. But at the end of the day, the public needs predictions that can reliably and quickly estimate the future state of the weather and the uncertainty associated with those events. Climate disasters and weather disasters are increasing over the years. We lose between 40 and 50,000 people each year to weather disasters. And it is our job as atmospheric scientists to make sure that the public is informed and that we continue to improve on these predictions. And when I say that machine learning has really been taken to by the community, I want to show you this figure. This is by Chase et al., 2022, 2023. And essentially what it's showing is the percentage of all papers within meteorology that now have something to do with machine learning. That's in the blue line. And to contrast that, just anything to do with severe weather. And essentially what this figure is showing is that machine learning is now outpacing studies on severe weather in meteorology, which means that the community has really recognized this as some potential for impact. And when students come to me or when I start to work with people investigating the machine learning field, I kind of frame up the medium to climate scale problem in 4 separate areas that my research has particularly impacted. And these are the 4 areas, or my 4 pillars of impact based on in atmospheric science. And we're sort of going to go through all 4 of them today and talk about some of the studies that I've conducted here. So the first impact is post-model run or post-processing. So this asks the question, how can machine learning complement our current NWP or general circulation models in post-model runs? So essentially the idea is we take our traditional physics-based model, we then apply some machine learning algorithm to the output. This improves the final prediction of the model. So we're trying to either improve model fidelity or model performance. We're either trying to downscale it by increasing the resolution, or we're doing some sort of communication or risk assessment there. So major areas of research in that. Secondly, we have this idea of scientific discovery, and this is asking the question, how is machine learning increasing our understanding of the Earth system? So what has the algorithm learned about the system, and can we employ either interpretable or explainable AI techniques in order to decompose some more of the physics of the atmosphere and gain a broader understanding of this space? Where the majority of my funding comes from and now is actually hybrid machine learning. So this asks the question, how can machine learning complement our current NWP or general circulation models in online runs? So in this paradigm, we're running the physics model, we're running the machine learning, they're talking to each other, the machine learning is influenced, what we call as the attractor state of the model, and it's adjusting it in some way to help improve the run. And typically we do this by leveraging either observations directly, data assimilation systems, or leveraging high resolution runs where we think the physics of the atmosphere are better defined. And finally, there's been a massive revolution in directly replacing our forward model. So can machine learning directly replace our current numerical weather prediction, or GCMs, and learn the physics of this forward model directly from the atmospheric dynamics or observing many states of the past atmosphere? And this emulation will allow us to immediately harness some of the computer architectures that will allow us to either increase uncertainty estimation or improve uncertainty estimation. So with that, I'm going to frame up the talk in sort of these 3 parts. We're going to spend a lot of time in part 1 and part 2. I'm then going to sort of talk about my current work and future work in part 3. And we got a lot of ground to cover today, so I'm going to launch right into it. So first off, model post-processing. So in forecast post-processing, we're developing a statistical linking function which maps the output of some numerical weather prediction model to some desired observations. So we're trying to improve model representation somehow of a forecasted field, and we're saying this is what you probably should have been forecasting. How can I improve this? So typically this relationship changes as forecast lead changes. So we have the model slipping into its own attractor, or a biased climatology. And really, this is the oldest form of supervised machine learning in the atmospheric scientists. And you can think back to model output statistics, Glenn and Lowry, 1972. And it's still an unbelievably active area of research, and it's been a productive area of research for me. As I've published a few studies in this region, I'm showing you some of the coverage there and sort of perspectives on the space. And today we're going to be talking about 3 of those studies. So our focus today will be on 3 publications which try to improve the representation of forecasted precip precipitation via model post-processing for the western US. And the studies are there. There's a lot of detail in them. We're going to do a kind of a brief overview. So if you have any questions, I encourage you chat with me, or I can send you these studies here. So the western US presents a pretty unique water problem. Precipitation in the west is proportionally variable from year to year, more than other parts of the United States. And this is a figure by Dettinger et al. In 2011, looking at precipitation observation statements, or tipping buckets, across the US. And essentially what it shows is the coefficient of variation within at those locations. And if I can interpret for you, this is the mean divided by the standard deviation. So essentially, or the standard deviation divided by the mean. So essentially, if you're in the pinks, you are every year about hitting your mean precip. If you're in the blues or the blacks, year to year, you're going to have a lot more variability in your change. So you can see that California particularly is subject to either a lot of droughts or a lot of wet years here. And what are those drought and wet years coming down to is we can show that it's really the highest or the largest impact events, or the 95th percentile and greater events, that are driving a lot of this year-to-year variability. So in the black line, you have total precip per water year. In the green line, this is less than 95th percentile precipitation. In the red line, you see the greater than 95th percentile for a particular catchment in California. And essentially what you can see is all of the year-to-year variability is represented in those 95th percentile and greater fractions. And what are those storms? Well, those are have been recently characterized as atmospheric rivers. So an atmospheric river is a narrow band of enhanced water vapor transport, typically associated with a low-level jet stream ahead of an extratropical cyclone. And really what you can think about this is just a measure of vapor transport within the atmosphere. We take the U and V winds, zonal meridional winds, multiply by the specific humidity, sum the column, and this is a representation of vapor transport, or IVT. And I'm showing that in hot colors here. And then in cool colors, you'll see, or in blues, you'll see the precipitation. And I'm going to click forward. You'll see a little GIF. And essentially, I want you to observe how often there is precipitation when there is not a strong vapor transport event impacting the western US. So essentially, these storms make landfall, rise, cool, precipitate out, and cause massive signals, especially within the California region. So we want to forecast these two states well. We want to forecast integrated vapor transport, and we want to forecast precipitation. So we're going to post-process those fields from a particular numerical weather prediction scheme. So I want to return to NWP really quick and talk about how we do it. So we have these initial condition state variables that we set out, U, V, T, Q, PS often. And then we feed those to a dynamics core and a physics core. And the dynamics is really discretizing the equations of motion, and the physics package is handling all the subgrid processes. We then take an initial forecast, march it out in time, and we have a forecast of some field. And this is called a deterministic forecast, or single forecast member. However, there's some major sources of uncertainty within the model. And the first one just rises from the chaos of the atmosphere. So we know from Lorenz that we have upscale air growth, and that unless our knowledge of the initial condition is exactly perfect, then we're going to have some deviation amongst the forecast space. It's going to explore its own attractor. However, the second area of uncertainty really comes from model deficiency. So we have these subgrid parameterizations that we know we're not capturing exactly well, or exactly perfectly. And additionally, we are doing a numerical approximation of the atmosphere. So we have some scheme that we are going to have to correct for here. So really what we're trying to do with post-processing is correct these two model deficiency here. But traditionally what we do to capture uncertainty is we launch what are called dynamic ensembles, in which we perturb the initial conditions. Sometimes we hand it off to varied physics packages or stochastic physics packages. And essentially we have a spread in our initial condition which leads to some uncertainty quantification at the end of the day. And essentially what this is an extremely computationally expensive solution to developing some of that uncertainty quantification. But it's the state of the art, and it's really been explored at how do we best create those initial conditions. But I came and did my weather center did my PhD at a weather center in which we only had a single deterministic run. So the idea that we wanted to essentially march forward was say, can we replace can we develop some uncertainty quantification via a deep learning algorithm by examining a historical forecast, a series of historical forecast misses, or a reforecast product. And essentially what we want to do is have the machine learning algorithm build our uncertainty in this space for us, and thus we can have some sort of probabilistic ensemble, or probabilistic metric in order to forecast these spaces. The second thing we want to do is actually have the network bias correct that forecast. So we showed in our 2019 study that there's a particular vision-based algorithm that is really good at post-processing a deterministic forecast. And what that was is a convolutional U-net. So a U-net essentially takes an input field and takes the full predictor space for this. In this case, we fed it 6 input variables. It then runs a series of convolutions, essentially decomposing the space into a really small latent variable, or latent representation, then builds it back up across the space, and it predicts a correction term to the atmosphere, or it predicts basically reconstructed forecast field. And in order to estimate uncertainty quantification, what we did is, rather than ask for a single member back, we asked for 2 fields which represent a mean and a spread of some prescribed distribution. And we tried many distributions, and essentially what you're trying to capture is the conditional forecast distribution. And as it turns out, the best calibrated forecast resulted from a zero truncated parametric, or zero truncated Gaussian distribution. So essentially this is all you can think about for IVT is there is no negative vapor transport. So we truncated 0, and we developed these distributions. And we characterized the CDF and PDF of those, and forecast that space. So in order to do that, you have to minimize some loss function. And the loss function that we are minimizing is called the continuous ranked probability score, or CRPS. And it's sort of a weird concept to wrap your head around, that you have a single forecast that acts as your observation, but you develop some uncertainty around it. And what CRPS is really doing is it's trying to match the distribution of 2 CDFs, or cumulative distribution functions. And this is the equation for it here, but what you can kind of look at is you have the output of the neural network, which essentially acts as a distribution here, so this red line, the CDF. And you take your observation, you treat it as a Heaviside function, and then the CRPS is really a representation of this area here. What you want to do is minimize that area, so you can imagine if you have a really certain forecast, essentially what the red line will start to look a lot like the blue line. That area will be minimized. And we can show that this is a proper scoring metric. So by calibrating this, or by minimizing this, we are calibrating the forecast itself. So we also need a numerical weather prediction model to forecast. So this is the one we use. It's produced by the Center for Western Weather and Water Extremes in San Diego, or at UC San Diego. And this is a version of the Weather and Research and Forecasting, or WRF, tuned for the West, so they call it West WRF. The time period that we do is we look at only the wet months, so December through March in California. That's our wet period. We then have a training of 30 years, and we do a cross-validation of 3 years to verify the model. It's got a varied spatial resolution, 9-kilometer nested grid, and then we have temporal resolution. We're just going to look at the 0 to 5 day forecast at 6-hour time steps. And for ground truth, we'll use a reanalysis product. So let me show you what one forecast looks like. So this is a forecast issued by the West WRF model on January 2nd, 2018. This is a 4-day forecast of IVT. We feed that plus a varied other fields in there. What spits out is a mean and a spread of a parameterized Gaussian distribution. And essentially what you can see is that the algorithm thinks that we should have more IVT closer to the coast, and that's really the most uncertain area represented there. How the forecast verified is like this. So essentially what we saw was a really increased IVT event. So we were right to sort of assume that this event should have been strengthened or intensified. And what we were able to do with this now, or what we can now offer as a forecast product, is probabilities above different thresholds, which can then inform the public whether they will be under different atmospheric river conditions. So this is the probability of over 350 units of IVT, or over 500 units of IVT, which puts you into different categories here. So we can add value to this forecast, essentially free now that we have trained our convolutional neural network. So this is on a single forecast. So in order to assess model health, we need to test it against a historical store of forecasts, and we wanted to test it against some of the current state-of-the-art post-processing techniques. So method 1, 2, and 3 are some of the post-processing techniques used every day, and additionally some neural networks there that work only on a local setting. And then additionally, we wanted to test it against an actual dynamic ensemble. So this is a different model called the Global Ensemble Forecast System, or the GEFS. And then we also calibrated the GEFS with a neural network, a local neural network, to see if we can improve over the dynamic ensemble here. And we're going to challenge our UNet versus these spaces. And if I can just show you a scorecard here, we have forecast lead on the x-axis and different methods on the y. And essentially, everywhere you see a blue marker, we are outperforming that in threshold-weighted CRPS. So this is CRPS that is measured only for extreme events, in this case, atmospheric river conditions. And what you can see is that over the traditional methods, we're pretty much universally outperforming it. Over the actual dynamic ensembles, for the first 48 hours, we do pretty well. Then we sort of hit a dry period where we are underperforming that ensemble before picking back up towards the end of the forecast time. And essentially what I can tell you about this, the middle period, is that the West Wharf kind of goes out to lunch there and has a fairly large error spread, and that's why we're seeing a large error there. So we couldn't quite post-process back to beat the GEFS comparatively. So we are assessing this CRPS metric, but we also want to see if it's a reliable forecast. And when I say reliable, I'm offering some metric of spread skill. So you can show mathematically that in a forecast system, the error should match the spread of the forecast. That should be a one-to-one relationship. However, typically what you see are either under-dispersive or over-dispersive forecasts, meaning that the spread is either too large or not large enough in order to quantify the error. And I'll show you a metric of that here, is that if you focus on the black line there, that's our CNN. And as you can see, it falls directly on that one-to-one line. Whereas all these other methods are either over or under dispersive. However, the CNN has really been calibrated well and performs reliably. So that was all for integrated vapor transport, but precipitation offers a potentially more difficult problem. It can either be on or off. It is not a smooth field. So can we alter this network in some way to now adjust and post-process precipitation and add uncertainty estimations for it? So essentially what we did is make a fairly simple change to it. We changed that characterization of the distribution from a 2 to a 3. So we're now going to characterize one more parameter. And that parameter will represent a shift in a gamma distribution. So our gamma distribution is what we're using to characterize the spread of precipitation. Then we add an extra parameter that essentially shifts the distribution below 0. If it's below 0, we're saying precipitation is off. Otherwise, we have some representation of precipitation being on here as we move this sensor-shifted gamma distribution. And I should say this is one of the most popular loss functions that have been fit for precipitation, but for very simple MOS-based systems here, proposed by Schur and Hamill in 2015. So looking at some metrics of whether we are outperforming the current state of the art, this is just accumulation over a single water year in a particular watershed, so the Yuba-Feather River watershed. And what I want you to take away from this is the UNet is in red, the observed precip is in black, and we're tracking that line fairly well, especially compared to the other post-processing methods. Additionally, we have some metrics of CRPS, and all you should really take away from this is that the higher scores are better here. And we can show that we are improving CRPS as well as some deterministic based methods when looking at just the mean itself, while still improving correlation, which is important there. So we're ensured that we weren't smoothing out the field. Finally, I want to look at just extreme events. So we know that these metrics are really good at getting the bulk statistics, but are the extreme events actually improved? So on the top column, we have greater than 95th percentile precipitation. On the bottom, we have greater than 99th percentile precipitation. And looking at spatially, we are looking in the greens, the UNet is better, and in pinks, the other metrics are better. And what you can see is there's a lot of green on that field. And the places that we are doing fairly worse is locations, either really dry locations, like out in the Nevada desert, or fairly dry locations, like the the Central Valley of the US. So there's room to improve our representation of some of that precipitation in those regions. Great. So with that, I want to bring to the end the part one, essentially saying that in a post-processing sense, these spatially aware deep learning algorithms can be used to debias atmospheric river forecasts and to add reliable uncertainty metrics at a fraction of the computational cost to a dynamic ensemble. The UNet generates accurate and reliable probabilistic IVT and precip forecasts that outperform other traditional methods. Great. And with that, I want to move on to part two, in which we are trying to use more interpretable neural networks or explainable neural networks in order to ask the question is how is machine learning increasing our understanding of the Earth system? And we want to interrogate what the algorithm has actually learned itself. And we'll frame this up in a paper that was recently submitted to GRL. And the first thing I want to highlight is this is work that we were able to bring on a student in the Significant Opportunities in Atmospheric Research and Science community. His name was Tony. We were able to teach him about some of these methods, me and my co-author Kirsten Mayer, and he was able to help run some of these forecasts, and we were really excited to get him on this paper with us. So today we're going to be talking about exploring the relative contribution of the MJO, or Madden-Julian Oscillation, and the El Nino Southern Oscillation to mid-latitude subseasonal predictability. And let's frame it up with a figure by Miel et al., looking at sources of predictability as you move across timescales. So on the x-axis, we have timescales here, and these are different sources of predictability within the atmosphere for different at different leads. So essentially, as you move out longer and longer into the week and the month, you can no longer predict the atmosphere with just traditional numerical weather prediction. It becomes less of an initial value problem. So folks start to look in this subseasonal to seasonal range, or S2S range, for different boundary condition forcings that will inform on predictability. And two of the ones that they commonly look at are the El Nino Southern Oscillation, which is a representation of tropical sea surface temperature anomaly, tropical wave or oscillation that tends to drive global weather patterns. And additionally, they look at the Madden-Julian Oscillation. And this is this time a sort of a heating pattern that oscillates across the equatorial band, again affecting global weather. And really the question we want to ask is, this figure is nice from a conceptual framework, but are these the right timescales for predictability across the contribution for Madden-Julian Oscillation and ENSO? And can we give a more nuanced look, especially for the Aleutian-Low teleconnection, and potentially inform more process-based studies or inform some of the statistical modeling work surrounding these two signals? So let's dive a little bit deeper into what these two signals are. So ENSO is an anomalous SST, or sea surface temperature pattern, with a return period of roughly 2 to 7 years. And ENSO influences global atmospheric circulation, creating these what are known as teleconnection patterns, which affect weather patterns far from the tropics. And what I'm showing here is a GIF that I made of an extended maximum covariance analysis, which essentially is showing the relationship between that pressure contours under the Aleutian Low and these Pacific sea surface temperatures. And you can see them developing over a season, a typical El Nino season. And what we're going to do is characterize this El Nino region with the Nino 3.4 index, which is essentially average over that box that I'm showing there. And essentially what has been studied over and over is that there are certain phases, or positive phases will drive a negative Aleutian Low, where negative phases will drive a positive Aleutian Low. So we're going to encode that index into our neural network. The second thing we'll look at is the Madden-Julian Oscillation. And this is a figure produced by the Adamus group showing the MJO, which is a heating pattern. You see a nice gill response from the tropics there. And its circulation response shown in the contours, the black contours. So the MJO is an eastward propagating equatorial pattern of anomalous heating circulating the Earth at roughly 30 to 60 day time period, and the MJO can affect weather patterns, again, in the mid-latitudes through teleconnections. So we need to encode this pattern somehow, and we're going to use the Wheeler and Hendon index to do it. So the Wheeler and Hendon index is essentially an EOF of that tropical space, in which it has these sort of coupled oscillating patterns. And what I'm showing here is a forecast of the Wheeler and Hendon index with RMM1 and RMM2 on the x-axis. And you can see a sort of eastward propagation in this what is known as a phase space. So we're going to take those two indices. Oh, I should mention, and it's been shown that there are certain phases that drive certain teleconnection patterns in the North Pacific. So we're going to take those two indices, the Wheeler and Hendon index and the Nino 3.4, and try to say something about the predictability at different leads of this Aleutian low pattern. And the data set we'll be using is the CSM2 pre-industrial control run. So this is produced by our group at NCAR. And the reason we're using it has a roughly good and a rough MJO and a roughly good ENSO teleconnection. And we verify this in the study, but it's been documented in a few other places. Additionally, we're able to use 300 years of data here, rather than if we operated on observations, we wouldn't have a long enough time signature. And then we compute the ENSO and MJO indexes within our target variable. And I want to say that we further confirmed our results on the ERA 5 data set, though I'm not going to be showing the confirmation of results there. So this is the neural network that we used in order to encode this predictability signal. It is developed by Argawal et al. In 2021. And essentially, what it is an inherently interpretable neural network. So what it does is it separates two streams of data inputs to really say, OK, this is where I am decomposing. This is the information I'm using in order to make the prediction that I'm making. So we have the ENSO network on the top. We feed it time at t0, or initialization time of forecast in the previous 15 days. We do the same for the MJO network. We also feed day of year information to there, because it's been shown there's predictability signals there. We then linearly combine these, and what we're trying to predict is the sign of the Aleutian low in this region that I'm showing here. So these two neural networks combine to linearly make the final prediction. And what we're doing is we're outputting probabilities in that final space. So we use a categorical cross-entropy metric in order to say, there's an 80% chance it will be positive and a 20% chance it will be negative. There's some sort of split there. The first thing I'll show you is just called a discard test, which examines the relationship between the network confidence and the skill. So essentially what you do is you bin the most confident predictions on the x-axis, saying that when the discrepancy between the positive and the output is greatest, you are more confident. And then on the y-axis, we have model skill. So what you can see very clearly is that there's this relationship between confidence and skill, meaning that we can say something about the really predictable states here on the far right side of the model. There are times when it is much more predictable and it is also accurate within that space. So we want to sort of examine these times over here. The first thing we noticed is that this is a histogram of the day of year for the total correct predictions versus the confident incorrect predictions. And I'm showing this binned by early winter to late winter here on the x-axis. So the day of year for the correct predictions is shown in gray. The day of year for the confident predictions is shown in blue here. And essentially, there is an extreme tendency to be more confident and more predictable in the late season. And I think there are people in this room that know that there are very fun dynamic reasons for why this should be the case. It really does make physical sense. And I have a paper looking at the signal to noise within large ensembles to show sort of why this would be the case. But it essentially comes down to jet dynamics and Rossby wave sourcing. But we're not going to go deep into that today. But just all that to say, this makes physical sense from an ENSO perspective. And then there was a nice paper by Jiabao Wang, which looked at sort of the anomalies in the early season and late season of the MJO teleconnection that did a similar physical dynamic relationship that was proposed in one of our papers that showed, again, a nice relationship, the late season versus early season. So looking at what else the network could really tell us. So what I'm showing here is an attribution diagram. So this is saying, essentially, at what time scales is the network using what sources of information in order to make its final prediction. And essentially what we saw is at long lead times, longer than 14 days and averaging windows, it was really leaning on ENSO. But what we were sort of surprised about is that even on the early lead times and with fairly small averaging windows of 2 days or so in the North Pacific, it was still really leaning on the ENSO prediction in order to make a short subseasonal forecast. So potentially there is more predictability there from a seasonal perspective or subseasonal perspective than previously we had thought. Additionally, I'm showing percent of network contribution for the really confident forecasts. So it turns out it's really leaning on the ENSO prediction for the very confident forecasts and less for the MJO network. However, if we look at this a little bit closer, we notice a distinct asymmetry between the sources of predictability given either positive or negative phases of this Z500 anomaly in the North Pacific. So essentially, if I can decompose this for you, the negative anomaly predictions, really confident with ENSO, meaning that there's a strong predictability forcing at all lead times. However, in the positive state, it's not. Essentially what this corresponds to is essentially saying that the El Nino forecasted teleconnection is much more predictable than the La Nina, and there are certain phases, particularly when the MJO is leading to positive phases, that it is much more predictable, or is at least an equal player in that field. So the one bummer about El Nino is it's not going to be an El Nino year every year. So we wanted to examine when are there states when the MJO is providing peaking predictability signals. So essentially what we did is we looked at ENSO neutral years. We then did cluster analysis on the most predictable MJO states. And what turned out is we found 3 unique clusters. And this is, I'm representing 2 of them, but I thought they were fairly interesting. So this is showing a phase diagram of the forecast. Essentially what this is showing is that when you have really strong MJO events that then decay off into a neutral state, you have a predictability peaking in the atmosphere, meaning that MJO is not going to move into an opposite phase and cause kind of destructive interference between the 2 states, but it goes really strong, shuts off, primes the atmosphere. So we're hoping to use this kind of analysis to look at more process-based studies to see how the models are actually representing certain MJO fields and ENSO relationships. The take-home messages were kind of shown throughout the slides, but I really want to focus on the caveats here. So we used indices to predict these. This could be much more informative if we use spatial representations of the actual precipitation associated with the MJO itself. I think we could say a lot more about what's being represented well and what's not being represented well. And these results are for CSM2, but the network seemed to show identical results when we applied it to the ERA 5 data set. So we have some confidence in it. And finally, I was able to work or contribute to a paper here that just was put out in 2023, very recently by Danny Du at CU Boulder. And she shows that the MJO has become and will become more predictable as we move into a future climate state. So this could potentially change some of these prediction relationships, or at least we can forecast those states more accurately. So with that, I want to move to part 3, or the last part of this talk, where I'm going to be focusing on some of my current work and looking at some future areas of research where I'm hoping to dive into. So part 3 really looks at, or the first part of part 3 is how can machine learning complement our current NWP schemes or GCMs in online runs. So this is, again, using that hybrid machine learning scheme in which the machine learning and the GCM are running at the same time and they're interacting with each other. So if we return to this figure from before, there are really 2 main sources of model deficiency that we're trying to address with using machine learning here. So how can we help address these errors, the subgrid parameterization and the numerical approximations? And there's a large funded project called M² lines, which I'm a part of. I'm an early career researcher in which we're trying to answer this exact question for climate modeling. And this is a slide provided by Lars Anna. And this shows sort of the 2 pathways in which we're attacking this problem. So one, we run either high-resolution runs or looked at direct model observations. We then encode those better represented physics in a neural network, and we run that online. And the second area in which I have active research in, which is sort of my bread and butter recently, is using data assimilation products or simple data assimilation, or simple nudging, really, in order to correct for structural errors and then reinsert these back into the model and thus improve the climate model state. And the idea really works like this. So this is a figure by Palmer and Weisheimer in 2011 showing a data assimilation system that has been applied to a healthy model up on top and a potentially biased model up on down bottom. And essentially what you can see is that the observations are in gray, and as we run the model out, the DA system, which is represented by the arrow there, is always forcing the model in one direction. So this would be like if your SSTs were too cool and you were trying to, the DA algorithm was consistently trying to push them in one direction, indicative of a model bias there. And really the thinking behind correcting total model bias is, although the amplification of this effect on, or this forcing on some bias will occur on the timescale of decades, meaning you can only assess model bias by looking at a 30-year run, 40-year run. The intrinsic timescale associated with this process is likely happening from time step to time step or in the local parameterization scheme. So it's really the accumulation of these errors that lead to some sort of downstream error. So can we build machine learning algorithms that look at the current model state and try to make a mapping between this state and the other? So Judith Berner and I just put out a paper showing that we could use both pretty intensive schemes, so full ensemble Kalman data assimilation systems, and nudging, and sort of accomplish the same thing for computationally much less computational power. So essentially, I'm just showing one metric here that we improved. This is a global precipitation throughout the months, and we're showing between 15 to 20% improvement, depending on the season, in a 30-year run of CSM. And where my current area of research is to develop a state dependence in this. And what we've done is we've taken a UNet that takes the full state of the atmosphere and predicts the increments that are coming out of the DA system. And what we have found is an architecture that really produces a good fit. So this is latitude on the x-axis, and it goes in the vertical the vertical levels of the atmosphere on the y-axis. And this is just showing the r² for that space. So essentially what we've done is we've written an algorithm that can predict the increments, and we're running it online in CSM now. And this used to have a nice figure showing my precipitation results, but I noticed that we had a top of atmosphere bias yesterday, so I took it out a few days ago. So the results are pending there. It looks like we've introduced another bias, and we want to address that more before I push it out. But really the thing I'm most excited about is that we have created a bridge between CSM and Python. And this took a long time to get done. And I have also Jim Edwards to thank, who is a software engineer. And we spearheaded this. But this GitHub branch, or this branch will go onto GitHub for a model release, and you'll be able to run Python directly and interact with CSM and interact with those Fortran modules. And if you want an early release of this, if you want to go do this, please email me. We're really looking for folks that want to insert these machine learning schemes into CSM and really get this up and running. So I'm really excited about that. So please do email me. And finally, I want to just touch on our work at NCAR and a team I'm leading to start to do some of this direct model replacement. So in this, we are taking a store of observations, the atmosphere, particularly the ERA 5, and marching those forward in time and trying to make the best weather model possible. And really what I want to say is that there's been an explosion of this area of research, not in small part to some of the science that's gone on at University of Washington. And these models are getting quite good. They are starting to compete with some of the state-of-the-art atmospheric models. And I should say there is a lot of debate in the community about whether they're being assessed correctly and whether we can really rely on the actual forecast assessments that we've done. But I will show this figure out of WeatherBench from RASP et al. That just came out that essentially assesses our state-of-the-art traditional models versus some of these pure machine learning-driven models. What you can see is anywhere in blue, the model is sort of out-competing the current state-of-the-art. And again, I should add that there are caveats to this, that not all people think they're being treated correctly. But I want to kind of go through a timeline of how I've seen this develop throughout our field. I think in 2015, when I first started my PhD, it is laughable to think that a deep learning model could replace the forward model. So it would really never happen. However, I think in 2019, a couple of studies came out, 2019, 2020, that said, it's starting to get a little interesting over here. And maybe we should start paying attention to this space. And then I've labeled this next phase the repeated existential crisis and denial phase, in which the community goes, what? Oh no. And then everyone has a model. Like literally every tech company put something out. And then there were more fair assessments being done. And if you were at the AMS in 2024, our annual meeting for meteorology, you will know that it sort of dominated the space. There was I was out at lunch and I was hearing people talk about these things that had no business talking about them. This is the exciting things to come, and I think the next phase of research is going to be really, really exciting, and it'll probably happen in the next 6 months at the way the pace of these things are moving. But I think there was a strong focus on the identification and tackling of key problems, specifically smoothing problems within these algorithms. I think coupling and ensemble and data assimilation, which I heard there's some data assimilation with these models going on at UW right now. And I'm really excited for the phase of predictability hypothesis testing, and I think it's coming really, really soon. So NCAR really wants to be involved in it, and I'm co-leading a team in which we are trying to democratize this process and make sure that students and faculty and anyone that has access to the NCAR machine will be able to run and hypothesis test and develop these models. So essentially, we're creating 3 different modules that are just about ready to go. We have a data handling in which we take our research archive stores. We then have modularized models. Right now, we have a vanilla UNet transformer. We have Fuqi running on this right now. And anyone with an allocation will be able to run these and then evaluate them. And we really want to make science-ready model architectures. And the real goal is a democratization of the space. So we want everybody to have access to this so that atmospheric scientists and computer scientists can work side by side, and you don't have to be sort of constrained to being at a large tech company or have a massive amount of compute. Use our compute. So a community machine learning numerical weather prediction model with open code, accessible, trainable. Pull and run the model in a few commands, and you will have all that data and code on your machine so you can be able to play. And this is the team that's sort of spearheading it right now. So with that, I will put up my sort of 4 pillars and say thank you and ask for questions.
Okay, do we have some questions?
I know you are an expert on DA. Could you tell me a little bit about the future of machine learning in DA for NWP?
I would not say I'm an expert on DA. I use the increments themselves. I have a good understanding of them, but I won't make the claim I'm an expert. I think there's a lot of interesting work, especially going on. NOAA has a team working on this right now. That how do we use the observations directly, translate into the field rather than working on these reanalysis fields. And I think the fact that these models run so quickly and we can develop some of these forward models, it's going to be a really interesting space. I don't want to comment on it too long. I want to save that for someone that is probably more of an expert in these, specifically ensemble Kalman techniques. So yeah, I'm going to punt that question to someone else. Apologize.
Yes.
Quick questions is that you in the part 1 you said that you use the standard deviation to estimate the uncertainty, right?
Yeah.
Yes. So as for the field, we most of the time we're considering the covariance to understand the uncertainty of this prediction field. Could you use this covariance information to understand the uncertainty in your work?
Yeah, I think it could be developed in there somewhere. I'd have to think exactly how to do it. So we are really characterizing these distributions because we know how to minimize these particular loss functions, and we know that calibrating them with these proper scoring metrics, we will develop a calibrated space. So that's really our motivation for using that. So I'd have to think exactly how to develop that from just a covariance perspective, but it sounds like a good idea.
Actually, I'm going to sneak a quick question in, and then we'll go, Dave. You had these graphs that suggested that El Nino could be far more helpful in S2S forecasts than the MJO. And it was hard to calibrate all of this, but we know there's big MJO fans for S2S. And I just wondered what your further elaboration might be on this question of what the MJO might really buy you, say, for S2S predictability.
So for the long range, I think the jury's out whether it's clear that we are predicting the MJO really well, the MJO signal itself. But then you have to mix with all the uncertainty on the atmosphere on top of that. So we'll get out to 6 days, we'll have this, bivariate correlation of 0.8, but what does that mean for the actual forcing? So you need to be able to really get those processes right in order to understand if that's going to influence the teleconnection and then go downstream. So I come out of a group that is very ENSO friendly. And I don't think that there is a rift. I don't think there's an actual rift between MJO and ENSO, but I think the fact that we are putting so much of our S2S hopes on the MJO when there can be additional sources of information and additional modulations to that signal, I think we need to get more nuanced rather than just trying to use. And I say that after saying just using 2 indices and predicting there, but I think we need to get much more nuanced with our conversation there before we can really make a statement about how useful it will be for predictability. Yeah.
Okay, great. Well, David was, and then Greg.
Well, this is probably a stupid question, but somebody's got to ask one. So, when you you had one forecast forward, and you built your, kind of post-processing neural net model. What would you get if you had a whole ensemble of those things, and you applied the same neural net model to each one of the ensemble members? Would it all? You see what I'm saying?
It's a really interesting question. Yeah. First off, and I took this figure out. Maybe it's still hidden. Let me see if I can. So the issue with a lot of our dynamic ensembles, especially on this short lead, is they're highly underdispersive. So they contain a lot of the same information over and over. And that's that's the reason we could really compete with these ensembles, is if we had a better calibrating system for the original, we wouldn't be able to take our deterministic member and beat a dynamic ensemble with it. So really, the good answer is develop a better either spread metric or an initial condition seeding such that we can develop ensembles across different time spaces that are calibrated and accurate. And that's why I'm very hopeful about these AI models, is that they're fast to run, and we can really calibrate spread and really start leaning into how do we build ensembles effectively, because we're no longer limited by compute. Or at least we can run them really, really fast. So I think there's going to be a lot of fun space to play in the ensemble initialization space. Yeah, that kind of answers your question.
Greg.
For large language models and the vision problem, there are scaling laws that have been known for at least 6 years that have provided a lot of confidence in the ability to provide investment to yield outcomes. I've seen very little of this in our field. There's Hint and Gilpin's paper from last year, over 100 plus low-dimensional dynamical systems, that this behavior will apply in that realm as well. But I don't know of anything in the high-dimensional setting. Do you have any ideas or thoughts about whether we can gain the same sort of confidence in scaling these models? Because they're tiny right now.
Yeah, exactly. I don't. A simple answer. I think it's a really interesting point, and you can think about all the parameters and the states of the atmosphere that we're supposed to estimate with these spaces. I think there's going to be a lot of future development. I'm excited to look at it, but yeah, I don't have an informed answer.
Jason.
Yeah, really interesting talk. In your part 3, you mentioned how a neural network can be used to learn some of the physics that the dynamic models don't fully understand. And you didn't really mention, I guess, the butterfly in the room, you know what I mean? Like, you had 2 sources of error, and one of them was chaos, and I'm just curious if you learned anything about a neural network's ability to learn about chaos.
Yeah, there is a nice paper that I think it's called "Do Neural Networks Have Butterflies?" or something to that effect, and they showed sort of a failing of this aperiodic motion within there. I don't think, when I'm talking about, I really am trying to correct for model deficiency and not for chaos, because specifically for the hybrid modeling, I was trying to apply this to climate model systems. So I don't care about predicting the weather. I care about getting the distributions right. I care about making sure we're representing our process as well. Do I think that there are ways that we can use these systems to inform on some of the chaos research? I think so, and I think folks have really been doing it. But yeah, it's a sort of a different question.
So you mentioned that the MJO might be more predictable in the future. And I think the biggest problem that I see right now in the machine learning itself with supervised learning is that you have a fixed training data set, and so your model learns based on this fixed data set. So because climate is changing, and so might be changing or will change. MJO is changing.
Yeah.
So the extreme events might change.
Yeah.
Do you see a possibility to create a unsupervised, maybe, machine learning or any other technique in the machine learning community that will be able to learn continuously as these things change? I know that there is a lot of work on that in neuroscience, but I'm not sure if we can use like something like that for like to tackle like many of these problems that we're facing.
Yeah, essentially you're talking about going out of sample, right? We're moving into a state that we haven't seen before. How do we deal with that? So there is a popular group of folks that are thinking about using more climate invariant variables that aren't projected to change more, and using those as input to the network, such that it helps learn these relationships without battling the dynamics there. But it is also just motivation to improve our physics-based models, such that we know we have a better representation, then we learn from those physics-based models, and we can sort of start to encode those into our space. So I think it really takes a community effort on both sides in order to start to address those questions. Yeah.
But in the machine learning itself, it's like it will be hard to.
Extrapolation is hard, yeah, no matter what. It's just going to be a hard problem. And I think if we can start to use techniques like equation discovery, which rather than using a black box method in order to move this forward, maybe we can actually distill some of the true physics out there. Like we've looked at some of the increments and they point towards distinct boundary layer problems. We used large and pond for our MO scheme, and there are inherent errors there. We can see sort of coupled errors. So I do have some faith that we'll be able to pull out some pieces that potentially will project into they will help us move out of distribution because they're not relying on extrapolation. So, yeah.
Okay, well, I think we're pretty well out of time here, so let's thank Will again.